everyone. Today we are going to discuss the topic of normalization and orthogonality of wave function in matrix form. In this topic in quantum mechanics wave function. So normalization on orthogonality of wave function is we already know. Normalization of wave function can be written in this form kept psi slash size is equal to integral form of phi star phi d tau. So we already know that phi star phi is will become integral over summation ij phi I star psi I, and similarly phi for these phi j and psi j with respect to ith particle and jth particle. So here this d tau will become here. So integral form of summation ij. See here actually the psi, we already know the wave function has some constant value, right? Here it has some value and here it has some value. So we are consider this value is some constant, right? So I am taking these constants ci star and psi I and cj. Here there is no psi. Here the star. So ci star psi I and cj psi j d tau. This term, if suppose in this term integral form of psi I and psi j into d tau, it can be written as epsilon I and j. So here I am substituting for these values epsilon I and j. So it will become summation ith and j particle ci star and cj. Here we are taking this form for this epsilon and ij. So this form is the length of the square magnitude. We are considering only ith particle. So jth particle is automatically neglected. So summation, this is the negative form of this, right? So I need a positive form. So that's why I put modulus here. So ci modulus whole square. And actually this is the normalization wave function and express square length of the magnitude of vector. Vector means it has some direction, right? Thus the normalization wave function corresponded to the unit length. This normalization into the matrix form of these. So I already put here. Where's that? Look at here. Integration phi star phi d tau. So I put this value integration phi star phi d tau. We are integrating these wave functions, so it will become, it has some constant value. So ci star c2 star up to cn, and similarly for psi, this psi value c1 c2 c3 up to cn. So it will become c prime and it will become c. So this multiplication of these product will become I. So if the normalization condition is a prime a equal to I, in similarly c prime c is also I. So this is the normalization of wave function in matrix form is proved here. And similarly orthogonality condition for a two wave functions of phi a and phi b, it can be written as, similarly we are already taking the equation of psi psi prime psi d tau, and similarly we are taking the two wave function. So it will becomes integration phi a star phi b d tau equal to 0. Why it's 0? Because orthogonality of the equation will become 0. We already know orthogonality condition is a prime a equal to 0. So we already know the equation phi a star phi b. We can able to substitute this value. So phi a, we are integrating these term ith and jth particle and it has some constant value. So ca I star psi a I, and similarly for b c b j psi bj. Here the d2 will become here. So I already said that integration and psi I and psi b into d2. This has the value of epsilon I and j. So here I am substituting this term for sigma epsilon ij. So it will become summation ith and jth particle cai and cbj epsilon ij. I already said that it is we are only considering the square length of the matrix, so we are neglecting jth particle. So it will become summation I cai star cbj. It is written in the form of matrix, so it will become ca1 ca2 up to can, and similarly cb1 and cb2 and cb3 up to cbn. So we are taking the whole term is c prime a and c prime z b. This is the Hermitian scalar product. It must be vanishes. So this equation is proved orthogonality conditions. So we are proving that normalization and orthogonality of wave function in matrix form. Thank you.